Hello everyone, so let's look at LeetCode problem number 310, minimum height trees. So in this question, we are given a graph, and for that we are given the matrix edges as we are usually given in a graph question. So for this example, let's say this is our matrix. So let's construct the graph. So for 3, 0, 3 is also connected by 1, 3 is connected by 2, 3 is connected by 4, and 4 is connected by 5. It is an undirected graph. Okay, so here is our graph. So what we have to do is, in this graph we notice that for nodes 0 to n minus 1, an array of n minus 1 edges is given. So for 6 vertices we will have 5 edges, and so there will be no cycles in the graph. So it is basically a tree. We are given here a tree, and we have to find the node of the tree such that its minimum height will be there. So for example, in this graph, let's say I choose this as my root. I will choose this 0 as my root. So what will be its height? It will be 1, 2 and 3. So its height will be 3. Okay, so let's write it down here for say our vertex and our height. For 0 it will be 3, for 1 it will also be 3, for 2 it will also be 3, for 3 it will be 2. Okay, for 4 also it will be 2, and for 5 it will be 1, 2 and 3. For 5 also it will be 3. Okay, so what we find from this example, that the vertex 3 and 4 has the minimum height. That means that if in the graph we choose our root to be 3 or our root to be 4, we will get the minimum height. So what we have to return is the vertex, or the which vertex should we choose as root so that our height will be minimum. Okay, so I was not able to solve this problem in the first go. What I was doing is applying BFS, as this is equally weighted graph. So I was applying BFS and going to every node. Like I was applying BFS to each node and getting the maximum height, and whichever nodes had the minimum height, I was returning them. But that was not an efficient solution, as we are given the constraint to be n is less than equal to 2 to the power 10 to the power 4. So applying BFS over all nodes, as BFS has a complexity of O of n, so for applying to all nodes it will be O of n square. Okay, so we cannot apply BFS here. BFS does not work here. Okay, so what we have to do is, we can think of it in another way, in terms of like topological sort, but not topological sort exactly, because topological sort is applicable only to the directed cyclic graph. This is not a directed graph, but if we know topological sort, so we can use that knowledge in this question. Okay, so it won't make a difference if you don't know what is topological sort, but I will attach a video of Striver or maybe Lovebubbles. You can watch it. And okay, so now let's move on to the approach of this problem. I saw this guy's solution. It was a really good solution. You can also take a look at his solution. So the first thing that you would have noticed is that for any given graph, what we are trying to do is try to pick it up from the middle. Okay, so the left side of that node and right side of that node will give us the minimum height. Okay, so in this example, we saw that our answer was 3 and 4, which was giving us the minimum height of 2. Okay, so these both vertices were giving us the minimum height of 2. So let me ask you a question. What are the maximum number of vertices that can give us the minimum height? In this particular case, it was 2. Okay, but this is the maximum. Any graph will have at most two such vertices that will give us the minimum height. You may ask why. Let's say for any example we have, there are three such nodes that give us the minimum height. The problem with that is, for let's say we have three nodes and these are giving us the minimum height. Okay, let's say h, h and h. But if you notice, if this is giving us the minimum height, it will have h children's here up till h height, it will have children's here or here up till h heights, and this will be an extra edge. Okay, so for this node it will actually should be h plus 1, and for this node, due to this edge, it will be h plus 1. For any three nodes this can never happen, because the middle node will give us the minimum height in that case. Okay, so now if we are clear with that, let's see how can we solve this problem or apply this in the code. Okay, so if we are given this graph, if you notice that what we can do is remove the leaf nodes. Okay, leaf nodes or the last nodes which has no childrens to them. So if we delete these nodes, okay, so now what we are left is 3 and 4, and these 3 and 4 now give us both the same minimum height, that is of 1 and 1. So that will be our answer. Let's take a bigger example. So let's say we have this 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say we remove the first leaf node. So this will be our leaf node, this will be our leaf node, this will be our leaf node, and this will be our leaf node. So let's remove them. We remove these nodes. Okay, so now you may ask, why are we removing the leaf nodes and will it not affect the minimum height? It will affect the minimum height value, not the node to be selected, as because if all the leaf nodes are deleted, then the minimum height or the height of each path will decrease by 1. So it won't affect the node that we are going to choose, which will have the minimum height. The minimum height won't The minimum height path will be itself, and the node that will be selected will be same. Okay, so now let's remove the next level leaf node. So this will be our leaf node, this will be our leaf node, and this will be our leaf node. So we will remove them. Okay, and now we are left with this as our leaf node and this as our leaf node. We will remove them and we will get 1 at the end. This will be our root node for this particular example. If we look at the solution also, so what 1 will give us height will be 1 2 3 1 2 1 2 3. Okay, so we see the height that 1 gives will be 3. Now you can check for any other node, for this one, 8 7 10 or 9. They all will give a height greater than 3. So that's why we cannot choose them. Okay, so now let's move to the pseudocode of this problem. How actually are we going to get these nodes and delete them? So now we will need three data structures: the adjacency list, the in degree array, and the queue. So let's first make the adjacency list, and while making the adjacency list we will also update the in degree array. So for adjacency list we have 3 and 0. This is our first edge. We will have to iterate this edges matrix. So adjacency of a list of 0 will contain 3 and 3 will contain 0. For 3 it will be 1, and for 1 we'll have to add 3. Now for this edge, 2 will be in 3 and 3 will also be in 2. Then for this, 3 will have 4 and 4 will have 3. So 3 and 4. And finally for this edge, 4 will have 5 and 5 will have 4. Okay, so we have made the adjacency list. Now while making the adjacency list, we will in the code also maintain the update the in degree array. So what you have to do is for every edge increase the in degree of both the vertices. So for this edge, for this 320 edge, what will happen is in degree of 3 will be increased to 1. Initially all of it will be 0 0 0 0. It will also be 0. It is increased by 1. So let's mark it 1. In degree of 0 will also be 1. In degree of 3 will increase by 1, so it will be 2. In degree of 1 will become 1. In degree of 2 and 3 will be increased by 1, so they will become 1 and 3. Then in degree of 3 and 4, so they will become 4 and 1. Now in degree of 5 and 4, so they will become 2 and 1. Okay, so now if you notice, if we mark these in degrees on the graph, so 0 will have in degree 1, 1 will have in degree 1, 2 will have in degree 1, 5 will have in degree 1. I'm calling it in degree. Actually, it should be called degree because it's not in degree, it's both in degree and out degree. So for 4 it will be 2 and for 3 it will be 4. Now what one thing to notice here is that for all the leaf nodes the degree is 1. So now you understand that we will remove those vertices that will have in degree 1. Okay, but for doing so, let's say we remove those vertices, we will left with 3 and 4, but we will have to update their in degree as well. Okay, so if we remove 0 from here, the in degree this will remove, and because this edge is gone, the in degree of 3 will be decreased by 1. So now it will become 3. Then this will be gone, so in degree will become 2. Then this will be removed, so in degree will become 1. And now in degree has become 1, so 3 now itself is a leaf node. Okay, now in when 4 will be returned, the in degree will be 1. Now 4 has also become the leaf node. So what we have to do is for each level of root nodes, for example in the first phase these will be our leaf nodes. As we can see, these are 1, so these will be our leaf nodes, so these will be removed first and then we will see what we have to do with 3 and 4. Okay, so what we will do is we will iterate this in degree array, and wherever we find the in degree to be 1, we will push that vertex into the queue. So we will push here 0, 1, 2 and 5. Okay, so as we push them into the queue, we will decrease them, or you can because when we again come back to in degree array, we should know that these are removed, so we will decrease them to 0. These are decreased to 0. Okay, now we will pop each element from the queue one by one and check all of its neighbors and decrease their their degree by 1. And as we decrease their degree by 1, if that element itself comes to have a degree of 1, that will be a leaf node and that will be added to the queue for the next phase. Okay, so now we removed 0 and we will see the adjacency list of 3. That's why we made the adjacency list. So adjacency list of 0 contains only 3, so 3 will be decreased by 1 and it will become 3. Okay, now let me now put a marker here so we know that this was our first phase. Okay, then we'll pop 1. 1 has 3 in its in degree, so in the adjacency list, so we will again decrement it by 1, so we will decrement it by 1, so it will become 2. Then we will pop 2. For 2 we have 3 in the adjacency list, so again it will become 1. And now this 3 has a in degree of 1, this has a in degree of 1, so we will have to push it into the queue, and when we push it into the queue we will also decrement it by 1 and make it 0 so that we don't come across it again as a leaf node. Then we'll pop 5. 5 has 4 as its neighbor, so 4's 1 degree will be reduced by 1 and it becomes 1, so it is also a leaf node, so we will push 4 in the queue. Now after each phase is completed, we should check that the nodes that are left, okay, the nodes that are left are are not greater than 2, because you can have either one or two such nodes which will give you the minimum height. So what happens is, at for any graph, when you remove its lowest level nodes, that is the leaf nodes, when you remove these, the degree will be decreased by 1 of all of its neighbors, so they will become, some of them will become leaf nodes, and then they will be pushed into the queue for the next phase. So in the first phase, what will happen is the lowest nodes, that these nodes will be removed, and in the next phase we'll have these nodes will be removed, and now we are left with only this one node, so this will be our answer. But instead, let's say we had two such nodes, okay, so let's say that we had another node, so this is our another node, and now if you see the in degree, you will understand, when you calculate the height, you will understand that these both will give us the minimum height. So now when you go and remove these level by level leaf nodes, you will remove them first, then these, then you will realize that you have now two nodes, and both will give us the minimum height, so we'll return these two nodes as the answer. Okay, so now let's see the pseudocode of this problem. So in the find minimum height function, we have two arguments, n and edges. So first we will make the adjacency list, so it will be vector int adj size n are the number of vertices, and we will also need a in degree vector, so vector int in degree, and it will be of size n. So first we will make the adjacency list. For making the adjacency list, we will have to traverse the edges matrix for int I is equals to 0, I less than edges dot size, or we can say n minus 1, because we are given here that we have edges n minus 1 number of edges, I plus plus. Then our vertex u will be edges of I0 and will be edges of I1. So basically this will be u and this will be v. Okay, so now we will add them to the adjacency list. So adj of u will be v, or it is vector, so it will be dot pushback v, and adj of v dot pushback, we will have a u. And now we also maintain the in degree, like initialize the in degree. So in degree of u plus plus and in degree of v will also be increased. Okay, so now we have made the adjacency list. We'll have our in degree updated. Now we will make a queue. Okay, so let's declare a queue. So q int, let's name it q, and what we will do here is, now we are pushing all vertices with in degree 1 in q. So for int I is equals to 0, I less than n, I plus plus, if we find the in degree of I equal to 1, we will push it into the queue. So q dot push I. So now those vertices will be pushed into the queue, and now we will pop elements from the queue, okay, until we have the left, or we can say left is a variable that we have basically mean to what are the number of vertices that are left. Okay, so you will understand it. Let's for now hold for a second. So left is equals to n, and now we will traverse the now we will pop elements from the queue and see their neighbors. So while left is greater than 2, you might have guessed why I have written here 2, if you remember the first point that I told you to remember. Now what left is signifying here is that if we have this graph, so now as you can see in this graph we have 7 vertices. So initially n will be 7. Now as we remove these in the first phase, that is, now when we are done with this one, our queue will contain these nodes, and these are the leaf nodes, or they have the in degree as 1. The other nodes have in degree greater than 0. So now in the queue we have pushed these many nodes. Okay, so now that we have kind of removed them, so we are left with only 4. So how we write it in the code, that we are left with left is equals to left minus the size of the queue. So queue dot size. Okay, now we will pop an element from the queue. So before popping the element, what I want you to understand, how many elements will be popped from the queue. We will not pop all the elements from the queue, okay, because as we are in a while loop, when we will pop, if we pop this one first, then in degree of this will become 1. It was 2 first, then it will become 1, and we will push that, but it should be removed in the next phase. Okay, it should not be removed now, it should be removed in the next phase. So what we will do here is, we will only pop the queue dot size, that is the current size of the queue, these many elements. Okay, so we'll have to save it in the variable, as because we pop the queue, its size will be affected. So let's say we have a variable s which contains queue dot size. Okay, now we have to pop s number of elements from the queue. So for int I is equals to 0, I less than s, I plus plus, what we are going to do is, we are popping an element, let's say current is equals to q dot front, then we pop the q, so q dot pop. So now the q is popped, and we will check all of its neighbor. Okay, so we are going to check all of the neighbors. So here let's say that we write for j in adjacency list of current, that is the element that we just popped, what we will do is, we'll decrease its in degree of j, minus minus, in degree of j will be reduced, and if the in degree is equals to 1, then we will q dot push j. Okay, So now that we have pushed it in the queue, the neighbors whose in degree has become 1, we will close this for loop and we will move to the next phase. Okay, now we'll move to the next phase, that is when we remove these nodes. Now we are left with these nodes in the queue. Okay, so our size was 3, so we have removed only these 3. Okay, so let's name them as 1, 2, 3, 4, 5, 6. So initially our queue was containing only 1, 2 and 3. Okay, then when we popped 1, another element 4 had its in degree becoming 1, so it was pushed into the queue. Then similarly this was popped and 5 was pushed into the queue, and when 3 was popped, 6 was pushed into the queue. And as we have decreased only 3, we have popped only 3 elements because our initial size of the queue or this batch was 3. So now we'll move to the next phase, where again it will check if the number of elements left are greater than 2, then only it will go, else we will end the loop, and whatever elements are there into the queue, that would be our answer. Okay, so let's let's dry run it for another iteration. Then we will have 4, 5, 6 into the queue, and now our left was first n, then because of these nodes it was n, then it became n minus 3, and now for this size again it will become n minus 3. N was here 7, then it became 4, and now it will become 1. The left has become 1, but the condition was checked earlier. Now it will go and actually remove these elements one by one and decrement the degree of this one, their neighbor. They have only one neighbor now, so if we see its degree would be 3, then when this will be removed, its degree will become 2. When this will be removed, its degree will become 1, and when its degree becomes 1, we push it into the queue. And now we pushed 1 into the queue, sorry, not 1, this nodes, let's say this is our m node, that's the minimum height node. When we push this node, then our batch here will now have 1 in the queue, and then 6 will be removed from the queue, which will decrease its in degree. Okay, and, but now we have this in the queue, and we will pop only these many elements in this batch, and now we have our left is 1, and we have the element in the queue which is only 1. So we will have to declare that this node, so not 1, this m node is our answer. So we will return this m node in a vector. Okay, so now in the last, as we have seen that after completing this while loop, we will have the elements left and less are either 2 or 1. So what we'll do is we will make an answer vector int answer. We will pop the queue while it's not empty, so while queue not empty, we'll pop it and push that element into the answer. So answer dot push back queue dot front, and now we have to pop its queue dot pop, and finally we will return our answer, and thus completing our find minimum height function. Okay, so this video, I hope that I was able to make you understand this problem. So okay, I will see you tomorrow. Bye.